Right now, as you're watching this video, you're looking at light that has traveled across billions of years to reach your eyes. But 13 billion light years away, floating in the cosmic darkness, there's something that, according to every law of physics, every model of cosmic evolution, and every theory we've built about how the universe works, simply cannot exist. And yet, there it is. Welcome back to The Weary Researcher. I'm thrilled you've decided to join me tonight as we explore a discovery so profound, so utterly bewildering, that it's forcing scientists around the world to question everything they thought they knew about the universe itself. Before we dive into this cosmic revolution together, I'd love to know where in the world you're tuning in from and what time it is in your corner of our pale blue dot. And I'd be incredibly grateful if you hit that like button and perhaps subscribe to join our community of cosmic truth seekers. Get ready. The journey begins now. What we're about to explore tonight isn't just another interesting astronomical discovery. This is a fundamental challenge to our understanding of existence itself. A cosmic paradox that threatens to rewrite the textbooks and force humanity to confront the uncomfortable possibility that we've been wrong about some of the most basic aspects of reality. The story begins with humanity's most ambitious attempt to peer back through time itself. The James Webb Space Telescope, floating serenely at a point in space called Lagrange 2, represents the absolute pinnacle of human technological achievements. This isn't hyperbole or excitement talking. This is the simple truth about an instrument so revolutionary that it has fundamentally changed our relationship with the cosmos. Picture an observatory unlike anything ever built. A telescope with a primary mirror spanning 6.5 meters across, composed of 18 hexagonal segments of gold-plated beryllium that work together with such precision that they can detect the heat signature of a bumblebee at the distance of the moon. The entire structure unfolds in space like a cosmic origami masterpiece, protected by a tennis court-sized sunshield that keeps its instruments colder than the vacuum of deep space itself. But Webb's true power isn't just in its size or its engineering elegance, it's in its ability to see wavelengths of light that have been stretched by the expansion of the universe itself. As light travels across cosmic distances, the expansion of spacetime stretches those photons from visible light into the infrared spectrum. Webb's infrared vision allows it to capture light that has been traveling since the universe was a mere infant, providing us with a direct window into cosmic history. When astronomers first conceived of this incredible machine, they had specific expectations about what it would reveal. They anticipated seeing the universe's first stars, modest gatherings of hydrogen and helium that ignited in the cosmic darkness perhaps 400 million years after the Big Bang. They expected to observe small primitive galaxies gradually assembling themselves through cosmic time, growing larger and more complex as billions of years passed. The conventional wisdom painted a picture of cosmic evolution that was orderly, predictable, and gradual. The universe began with the Big Bang 13.8 billion years ago. For the first few 100 million years, space was filled with nothing but cooling gas and the invisible scaffolding of dark matter. Slowly, gravity began its patient work, pulling matter together into the first stars and tiny galaxies. These early cosmic structures would be small and chaotic, nothing like the magnificent spiral galaxies we see today. Over billions of years, these primitive building blocks would merge and grow, gradually assembling into the complex cosmic architecture we observe in the local universe. It was a story of patient cosmic construction, where each stage required vast amounts of time to unfold. The universe was supposed to follow a careful timeline, with massive, mature galaxies appearing only after billions of years of gradual assembly. This understanding wasn't just theoretical speculation, it was built on decades of observations with the Hubble Space Telescope, sophisticated computer simulations of cosmic evolution and our best theories about how gravity, dark matter, and ordinary matter interact across cosmic scales. Every model, every calculation, every prediction pointed to the same conclusion. The early universe should be simple, and complexity should emerge gradually. Webb was designed to confirm and refine this picture. Astronomers expected to see baby galaxies in the process of formation, primitive star clusters slowly organizing themselves into larger structures, and perhaps catch glimpses of the very first stars igniting in the primordial darkness. These observations would fill in the missing details of cosmic evolution, providing the final pieces of a puzzle that seemed nearly complete. But the universe, as it turns out, had other plans entirely. When Webb began its deep observations of the most distant reaches of space and time, what it revealed was so shocking that astronomers initially questioned their own data. Instead of small primitive galaxies struggling to form in the cosmic darkness, Webb discovered massive, mature galaxies that appeared to be thriving when the universe was barely 500 million years old. These weren't the modest collections of stars that theoretical models predicted. These were cosmic monsters, galaxies containing hundreds of billions of stars, rivals to our own Milky Way in terms of mass and complexity. And they were sitting there in the early universe as casually as if they had every right to exist, completely oblivious to the fact that they were breaking every rule in the cosmic playbook. Dr. Erica Nelson from the University of Colorado Boulder captured the astronomical community's bewilderment perfectly when she said, "It's bananas. You just don't expect the early universe to be able to organize itself that quickly. These galaxies should not have had time to form. The numbers are staggering. To build galaxies of this size in the time available, these cosmic structures would have needed to form stars at rates hundreds of times faster than anything we observe in the modern universe. The Milky Way, despite being a large and active galaxy, forms only about 2 new stars per year. These early cosmic monsters would have needed to forge hundreds of new stars annually for hundreds of millions of years to achieve their observed masses. But the mystery deepens even further. These ancient galaxies don't just contain vast numbers of stars, they contain the wrong types of stars entirely. Webb's spectroscopic observations reveal the presence of mature, evolved red stars in galaxies that formed when the universe was supposedly still in its infancy. Red stars are the elderly citizens of the cosmic community, stars that have had hundreds of millions of years to age and cool from their initial hot blue youth. Finding old stars in young galaxies creates a temporal paradox that challenges our understanding of stellar evolution itself. These red stars would have required vast amounts of time to evolve from their initial, massive, blue giant phases. Yet they appear in galaxies that formed shortly after the cosmic dark ages ended, when the universe had barely begun to organize itself into complex structures. The implications extend far beyond just these individual discoveries. Webb has identified over 300 objects that are significantly brighter than theoretical models predict they should be. This isn't a handful of anomalous cases that might be explained away as unusual circumstances or observational errors. This represents a systematic discrepancy between our theoretical expectations and observed reality. Among these discoveries are objects that astronomers have nicknamed little red dots and red monsters, cosmic entities so unusual that scientists aren't entirely certain what they're looking at. Some of these objects might not be galaxies at all in the traditional sense, but entirely new categories of cosmic structures that we lack the theoretical framework to understand. One particularly extreme case has been dubbed the cliff by researchers, representing the most massive and earliest galaxy yet discovered. This single object contains nearly as much stellar mass as the modern Milky Way, yet it existed when the universe was less than 700 million years old. The very existence of such a massive, mature galaxy so early in cosmic history suggests that our fundamental understanding of how the universe evolved from simplicity to complexity is profoundly incomplete. But perhaps the most disturbing discovery of all is Webb's detection of organized disk galaxies in the early universe. Current theories predict that early galaxies should be chaotic, irregular collections of stars shaped by violent mergers and interactions. The pristine spiral structures that characterize galaxies like the Milky Way are thought to be fragile arrangements that require billions of years of stable evolution to develop and maintain. Yet Webb has found over 1,600 disk galaxies in the early universe, organized spiral structures that somehow managed to form and maintain their delicate architecture despite existing in what should have been a chaotic, merger-rich environment. These findings suggest that the early universe was far more orderly and stable than our theories predict, capable of supporting sophisticated galactic structures that current models cannot explain. The discovery has forced astronomers to confront an uncomfortable truth. Either our understanding of cosmic evolution is fundamentally flawed, or we're witnessing evidence of physical processes that we haven't yet discovered. Both possibilities are equally unsettling for scientists who have spent decades building theoretical frameworks that seem to successfully explain cosmic history. Some researchers have proposed that these observations might be evidence of exotic physics operating in the early universe. Perhaps dark matter behaved differently in the primordial cosmos, allowing structures to form much more rapidly than current models predict. Others suggest that cosmic inflation, the brief period of exponential expansion that occurred immediately after the Big Bang, might have created initial conditions that were far more conducive to rapid structure formation than we previously realized. There's also the possibility that our measurements of cosmic distances and ages are systematically incorrect, though this explanation seems increasingly unlikely as multiple independent observations continue to confirm Webb's findings. The telescope's unprecedented precision and the consistency of its observations across different regions of the sky make measurement error an improbable explanation for such widespread anomalies. More intriguing is the possibility that we're seeing evidence of entirely new physics, fundamental processes that only operated in the extreme conditions of the early universe. Perhaps the laws of gravity themselves functioned differently when the cosmos was young and dense, allowing matter to organize itself in ways that are impossible under modern conditions. These discoveries represent more than just challenges to specific astronomical theories. They strike at the heart of our confidence in the scientific method itself. For decades, astronomers have built increasingly sophisticated models of cosmic evolution, validated by observations and refined through careful theoretical work. The apparent success of these models in explaining the structure and evolution of the local universe gave scientists confidence that they understood the fundamental processes governing cosmic development. Webb's observations suggest that this confidence may have been premature. The universe appears to be far stranger, more complex, and more mysterious than we imagined. Instead of confirming our theories, Webb is revealing that some of our most basic assumptions about cosmic evolution may be wrong. This scientific crisis extends beyond astronomy into fundamental physics. Our understanding of gravity, dark matter, and the behavior of matter under extreme conditions underpins not just cosmology, but much of modern physics. If these cosmic observations require new physics to explain, the implications could reshape our understanding of reality at the most fundamental level. Yet there's something profoundly beautiful about this moment of scientific uncertainty. We're witnessing the universe reveal secrets that we never knew existed, forcing us to expand our conception of what's possible in the cosmos. These discoveries remind us that despite all our technological achievements and theoretical sophistication, the universe still holds mysteries that can surprise and humble us. The questions these findings raise are as exciting as they are challenging. Are we looking at evidence that the Big Bang timeline itself needs to be revised? Do these observations suggest that dark matter and dark energy behave differently than we've assumed? Are we seeing the signatures of cosmic processes that we haven't yet imagined? As we continue this exploration into the deepest mysteries revealed by humanity's most powerful observatory, we'll delve deeper into each of these possibilities, examining what they might mean for our understanding of existence itself. The universe has just revealed that it's far stranger than we ever dared imagine, and we're only beginning to grapple with the implications of what Webb has shown us lurking in the cosmic darkness. The deeper Webb peers into the cosmic abyss, the more it becomes clear that we're not just looking at a few anomalous objects scattered across the early universe. We're witnessing what appears to be a systematic breakdown of everything we thought we understood about how reality itself came into being. Consider the sheer audacity of what these observations are telling us. When we look at the most distant galaxies Webb can detect, we're seeing light that began its journey when the universe was barely 3% of its current age. These photons have been travelling for over 13 billion years, carrying within them a record of cosmic conditions that existed when the universe was still learning how to be a universe. What that ancient light reveals should be impossible. Instead of the cosmic nursery we expected to find, filled with the tentative first steps of stellar birth and galactic assembly, Webb shows us a universe that hit the ground running at full sprint. These early epochs, which should represent humanity's view of cosmic infancy, instead reveal a cosmos already mature beyond our wildest theoretical predictions. The most disturbing aspect of these discoveries isn't just that early galaxies are massive, it's that they're sophisticated. Webb's spectrographic analysis reveals chemical signatures that speak of complex stellar populations, multiple generations of star formation, and enrichment processes that should have required billions of years to unfold. We're seeing evidence of cosmic chemistry that tells the story of stellar death and rebirth, of supernovae that scattered heavy elements through space, of gas clouds enriched with the ashes of previous stellar generations. This chemical complexity presents perhaps the most profound challenge to our understanding of cosmic evolution. The universe began with nothing but hydrogen and helium, the simplest elements on the periodic table. Everything heavier, from the carbon in our bodies to the iron in our blood, had to be forged in the nuclear furnaces of stars and scattered through space when those stars died explosive deaths. This stellar alchemy takes time. Massive stars live fast and die young, but even the most massive stars require millions of years to evolve from birth to supernova death. The heavy elements they produce must then be incorporated into new generations of stars, creating an evolutionary chain that should unfold over hundreds of millions of years at minimum. Yet Webb is detecting these heavy elements in galaxies that formed when the universe was supposedly too young for such complex chemistry to have occurred. It's as if we're finding evidence of a cosmic civilization in geological strata that predate the emergence of life itself. The timeline simply doesn't add up, and the discrepancy is too large and too systematic to explain away as measurement uncertainty. Among the most puzzling of these discoveries are objects that astronomers have struggled even to classify. Take, for instance, the mysterious entities that researchers have dubbed little red dots. These objects appear as tiny points of light in Webb's deepest images, but their spectroscopic signatures suggest they contain enormous amounts of mass compressed into remarkably small volumes. Initially, astronomers assumed these were distant galaxies, perhaps viewed at unusual angles or obscured by cosmic dust. But deeper analysis revealed something far more extraordinary. These objects might not be galaxies in any sense we understand the term. Instead, they could represent an entirely new category of cosmic structure, one that doesn't fit into our existing taxonomies of astronomical objects. The leading hypothesis suggests these might be black hole stars, theoretical objects that exist at the boundary between stellar physics and the exotic realm of supermassive black holes. Unlike ordinary stars which generate energy through nuclear fusion in their cores, these hypothetical objects would be powered by the accretion of matter onto supermassive black holes at their centers. The concept challenges our understanding of how supermassive black holes could have grown to such enormous sizes so early in cosmic history. Traditional theories suggest that these cosmic monsters should require billions of years to accumulate their mass, growing gradually through the accretion of surrounding material and the occasional merger with other black holes. But if black hole stars existed in the early universe, they could provide a mechanism for rapid black hole growth that bypasses the usual evolutionary bottlenecks. These objects could represent a phase of cosmic evolution that has no modern analogue, a period when the universe operated according to rules that we're only now beginning to glimpse. The implications extend far beyond individual objects to challenge our understanding of cosmic structure formation itself. Webb has revealed that the early universe wasn't just more active than we expected, it was more organized. The telescope has identified over 1,600 disk galaxies in epochs when such organized structures should have been impossible to form or maintain. Disk galaxies, like our own Milky Way, are engineering marvels of cosmic architecture. Their spiral arms represent density waves that propagate through the galactic disk, organizing stellar birth and maintaining structural coherence across hundreds of thousands of light years. These delicate patterns are easily disrupted by gravitational interactions, mergers, or encounters with other galaxies. Current theories predict that the early universe should have been a chaotic place, filled with violent galactic mergers and interactions that would have prevented the formation of such organized structures. The high density of matter in the young cosmos should have created a cosmic demolition derby, where galaxies collided and merged so frequently that stable disk structures could never establish themselves. Yet Webb reveals a different story entirely. These early disk galaxies appear to have formed their spiral structures and maintained them despite existing in what should have been a hostile environment. This suggests either that the early universe was far more stable than our models predict, or that disk galaxies are far more resilient to disruption than we've assumed. The discovery has profound implications for our understanding of dark matter, the invisible substance that comprises roughly 85% of all matter in the universe. Dark matter provides the gravitational scaffolding upon which ordinary matter assembles itself into galaxies and larger structures. The behavior of dark matter in the early universe should determine how quickly and efficiently galaxies could form. If Webb's observations are correct, dark matter must have been far more effective at organizing itself into large-scale structures than current models predict. This could mean that dark matter particles interact with each other or with ordinary matter in ways we haven't discovered, or that the properties of dark matter itself were different in the extreme conditions of the early universe. Some researchers have proposed that these observations might be evidence of modifications to our understanding of gravity itself. Einstein's general relativity has been tested extensively in the solar system and in nearby cosmic environments, but the extreme conditions of the early universe represent a regime where our theories have never been directly validated. Perhaps gravity behaves differently on cosmic scales or in the high-density environments that characterize the young universe. Modified theories of gravity, developed to explain the apparent effects of dark matter and dark energy, might provide mechanisms for accelerated structure formation that could account for Webb's observations. Another possibility involves cosmic inflation, the brief period of exponential expansion that occurred in the first fraction of a second after the Big Bang. Inflation is thought to have stretched quantum fluctuations in the primordial universe to cosmic scales, creating the density variations that eventually grew into galaxies and galaxy clusters. Most models of inflation predict that these initial density fluctuations should be relatively modest, providing gentle seeds for structure formation that would grow gradually under the influence of gravity. But perhaps some models of inflation could produce much larger initial perturbations, giving structure formation a head start that would allow massive galaxies to form much earlier than conventional theories predict. These theoretical possibilities represent more than just technical adjustments to existing models. They point toward a fundamental revision of our understanding of cosmic history, one that would require rewriting textbooks and recalibrating our conception of how the universe evolved from its initial simplicity to its current complexity. The psychological impact of these discoveries on the astronomical community cannot be overstated. Imagine spending your career building theoretical frameworks that seem to successfully explain the cosmos, only to have the universe itself reveal that your carefully constructed models might be fundamentally incomplete. It's both humbling and exhilarating, a reminder that the cosmos still holds secrets that can surprise even our most sophisticated attempts to understand it. Webb's revelations also raise profound questions about the nature of scientific knowledge itself. How confident can we be in our theories when direct observation of the phenomena they're supposed to explain wasn't possible until now? The early universe has been a theoretical playground for decades, with competing models validated primarily through their ability to explain indirect observations and their mathematical elegance rather than direct confirmation. Now that we can actually observe the early universe directly, we're discovering that reality is far stranger than our theories predicted. This doesn't represent a failure of the scientific method, but rather its ultimate success. Science progresses through the constant interplay between theory and observation, with new discoveries forcing revisions to existing understanding and opening up entirely new avenues of inquiry. The beauty of Webb's discoveries lies not just in their challenge to existing theories, but in their revelation of cosmic complexity we never imagined. Each new observation adds layers of mystery to our understanding of the universe, revealing depths of cosmic evolution that we're only beginning to explore. These findings remind us that we live in a universe far more dynamic, creative, and mysterious than we dared imagine. The same cosmic processes that forged these impossible early galaxies eventually led to the formation of our own solar system, our planet, and ultimately to the emergence of consciousness capable of contemplating its own cosmic origins. As Webb continues its observations, pushing ever deeper into cosmic history and revealing ever more impossible objects, we find ourselves witnesses to a revolution in human understanding. We're not just observers of cosmic evolution, we're participants in the universe's ongoing project of self-discovery, using instruments of unprecedented power to peer back through time and witness the impossible becoming possible in the infinite creativity of the cosmos. The story is far from over. Each new Webb observation brings fresh surprises, new challenges to our understanding, and new opportunities to expand our conception of what's possible in this strange and wonderful universe we call home. The impossible has become undeniable, and we're only beginning to grapple with what that means for our place in the cosmic story. But the revelations don't stop there. As Webb's observations accumulated and astronomers began to comprehend the full scope of what they were seeing, an even more disturbing pattern emerged. The telescope wasn't just finding a few anomalous objects scattered across the early universe, it was discovering that anomalous objects might actually be the norm. In a systematic survey of the deep universe, researchers identified 300 objects that are significantly brighter than any theoretical model predicts they should be. 300? This isn't a statistical fluke or a handful of unusual cases that might be explained away as rare exceptions to general rules. This represents a fundamental mismatch between our understanding of cosmic evolution and what actually occurred in the early universe. Each of these objects challenges our theories in its own way. Some appear to be massive galaxies that formed impossibly early. Others seem to be entirely new categories of cosmic structures that don't fit into any existing classification scheme. Still others appear to be ordinary objects that are somehow generating far more energy than should be possible given their apparent age and composition. The systematic nature of these discoveries forces us to confront an uncomfortable possibility. Perhaps the problem isn't with a few unusual objects, but with our fundamental understanding of how the universe works. Perhaps we've been operating under assumptions about cosmic evolution that are simply wrong, and Webb is revealing the true nature of reality for the first time. Consider what this means for our confidence in the scientific enterprise itself. For decades, astronomers have built increasingly sophisticated models of the universe, using the most advanced mathematics and the most powerful computers to simulate cosmic evolution across billions of years. These models seem to work beautifully, explaining the large-scale structure of the nearby universe and making predictions that appeared to be validated by observations. The apparent success of these theoretical frameworks gave scientists confidence that they understood the fundamental processes governing cosmic development. Dark matter provided the invisible scaffolding for structure formation. Dark energy drove the accelerating expansion of the universe. Gravity pulled matter together into increasingly complex arrangements over cosmic time. The picture seemed complete, elegant, and satisfying. Webb's observations suggest that this confidence may have been premature. The universe appears to be operating according to rules we haven't discovered, following evolutionary pathways we never imagined, and achieving levels of complexity we thought were impossible given the time constraints of cosmic history. Among the most puzzling discoveries are objects that researchers have nicknamed red monsters, three extremely massive and dusty galaxies that existed in the first billion years after the Big Bang. These cosmic behemoths challenge our understanding not just of galaxy formation, but of the very timeline of cosmic chemical evolution. The presence of substantial amounts of dust in these early galaxies is particularly bewildering. Cosmic dust consists primarily of heavy elements like carbon, silicon, and iron, elements that can only be produced in the nuclear furnaces of stars. When massive stars reach the end of their lives and explode as supernova, they scatter these heavy elements throughout space where they can condense into the tiny grains we observe as cosmic dust. This process of stellar nuclear synthesis and dust formation should take time. Multiple generations of stars must live and die to produce significant quantities of heavy elements. The dust grains themselves require specific conditions to form and survive in the harsh environment of interstellar space. Current models suggest that substantial dust production should require several 100 million years of stellar evolution at minimum, yet Webb is detecting dust-rich galaxies that appear to have formed when the universe was only a few 100 million years old. The timeline doesn't allow for the multiple stellar generations that should be necessary to produce such dust-rich environments. It's as if we're finding evidence of advanced metallurgy in civilizations that predate the discovery of fire. The chemical implications extend beyond dust to the entire spectrum of heavy elements that Webb detects in these early galaxies. Spectroscopic analysis reveals the signatures of oxygen, nitrogen, carbon, and even heavier elements that should not exist in significant quantities so early in cosmic history. Each of these elements tells a story of stellar death and rebirth, of cosmic recycling processes that enrich the universe with the building blocks of planets and life. Finding such chemical complexity in the early universe suggests that stellar evolution proceeded at a pace far exceeding anything we observe in the modern cosmos. Either stars lived and died much more rapidly in the primordial universe, or there were entirely different mechanisms for element production that we haven't discovered. Some researchers have proposed that the first generation of stars, known as population 3 stars, might have been fundamentally different from anything we see today. These primordial giants, formed from the pristine hydrogen and helium left over from the Big Bang, could have been hundreds or even thousands of times more massive than typical modern stars. Such supermassive stars would have lived incredibly brief lives, perhaps only a few million years, before exploding as hypernovae with energies that dwarf ordinary supernovae. These cosmic detonations could have instantly enriched vast regions of space with heavy elements, providing the raw materials for rapid dust formation and subsequent generations of star formation. But even this exotic scenario struggles to explain the full scope of what Webb observes. The chemical abundances in these early galaxies don't just indicate rapid element production. They suggest complex chemical evolution involving multiple cycles of star formation, stellar death, and gas recycling. These processes should require not just time, but specific environmental conditions that allow gas clouds to cool, collapse, and reform into new stellar generations. The puzzle deepens when we consider Webb's discovery of what astronomers call dormant or sleeping beauty galaxies in the early universe. These objects appear to have undergone rapid bursts of star formation, followed by sudden periods of quiescence, where stellar birth essentially shut down entirely. The existence of dormant galaxies in the early universe contradicts every expectation about how young galaxies should behave. Early galaxies should be voracious consumers of gas, converting available material into new stars at prodigious rates. The high densities and frequent interactions characteristic of the young universe should have provided abundant fuel for continuous star formation. Instead, Webb finds galaxies that appear to have experienced boom and bust cycles of stellar birth, periods of intense activity followed by mysterious shutdowns. This suggests that mechanisms for regulating star formation were already operating in the early universe, despite the very different physical conditions that existed at that time. The most likely explanation involves feedback from supermassive black holes at the centers of these galaxies. When black holes actively accrete matter, they can generate enormous amounts of energy in the form of jets and radiation that heat or expel the surrounding gas, effectively shutting down star formation. But this explanation creates its own puzzles about how supermassive black holes could have grown to such sizes so early in cosmic history. The traditional picture of black hole growth involves a gradual process of accretion and mergers spanning billions of years. Stellar mass black holes, formed from the collapse of massive stars, slowly, occasionally, they merge with other black holes, accumulate mass by consuming surrounding material. Growing larger through these cosmic collisions, over vast periods of time, some of these objects eventually reach masses millions or billions of times that of our Sun. But Webb is finding evidence of supermassive black holes that appear to have achieved enormous masses when the universe was still in its infancy. These cosmic monsters seem to have grown at rates that approach or exceed theoretical limits for black hole accretion, suggesting either that our understanding of black hole physics is incomplete or that entirely different mechanisms were operating in the early universe. Some of Webb's most perplexing discoveries involve objects that might not be galaxies at all in any conventional sense. Among these are the mysterious little red dots that appear as tiny points of light but contain spectroscopic signatures, suggesting enormous masses compressed into remarkably small volumes. Leading theories suggest these might be black hole stars, hypothetical objects powered not by nuclear fusion, but by the accretion of matter onto supermassive black holes at their centers. These exotic structures would represent a phase of cosmic evolution that has no modern analogue, a period when the universe experimented with forms of organization that we're only now beginning to glimpse. The concept of black hole stars offers a potential solution to the mystery of rapid supermassive black hole growth in the early universe. If such objects existed, they could provide mechanisms for accelerated black hole evolution that bypass the usual constraints on accretion rates and growth timescales. But black hole stars would also represent something even more profound, evidence that the early universe operated according to physical principles that we don't fully understand. These objects would exist at the boundary between stellar physics and the exotic realm of general relativity, in regimes where our theoretical understanding becomes uncertain and untested. The very existence of such objects would suggest that the early universe was not just more active than we expected, but more creative. It would indicate that cosmic evolution explored possibilities that modern conditions can't support, experimenting with forms of matter and energy organization that push the boundaries of what we thought was physically possible. Webb's discoveries also challenge our understanding of cosmic structure formation on the largest scales. The telescope has revealed that the early universe contained not just massive individual galaxies, but organized systems of galaxies that appear to have formed much earlier than theoretical models predict. Galaxy clusters, the largest gravitationally bound structures in the universe, should require billions of years to assemble from smaller components. Current models suggest that these cosmic cities should be relatively rare in the early universe, with most structure formation occurring gradually over cosmic time, as smaller objects merge to form larger ones. Yet Webb finds evidence of massive galaxy clusters and protoclusters that existed when the universe was less than 2 billion years old. These structures appear to contain dozens or hundreds of galaxies organized into coherent gravitational systems, suggesting that large-scale structure formation proceeded much more rapidly than current theories predict. The implications extend beyond individual clusters to the cosmic web itself, the vast network of filaments and voids that defines the large-scale structure of the universe. This cosmic architecture is thought to emerge gradually from the gravitational amplification of tiny density fluctuations left over from cosmic inflation. If Webb's observations are correct, the cosmic web must have organized itself much more rapidly and efficiently than standard models suggest. This could indicate that the initial density fluctuations were larger than we've assumed, that dark matter behaves differently than our theories predict, or that entirely different mechanisms were responsible for structure formation in the early universe. The cumulative weight of these discoveries creates a crisis of confidence that extends far beyond astronomy into fundamental physics itself. Our understanding of gravity, quantum mechanics, and the behavior of matter under extreme conditions forms the foundation not just of cosmology, but of much of modern science. If Webb's observations require new physics to explain, the implications could be revolutionary. We might be witnessing evidence of modified theories of gravity, exotic properties of dark matter, or quantum effects operating on cosmic scales. The universe might be teaching us that our most fundamental assumptions about the nature of reality need to be revised. Yet there's something profoundly beautiful about this moment of scientific uncertainty. We're living through a period of discovery that may be as significant as the Copernican revolution or the development of quantum mechanics. The universe is revealing aspects of itself that we never suspected existed, forcing us to expand our conception of what's possible in the cosmos. These discoveries remind us that science is not a collection of final answers, but an ongoing dialogue between human curiosity and cosmic mystery. Each new observation opens up fresh questions, new avenues for exploration, and new opportunities to deepen our understanding of existence itself. The questions Webb has raised are as profound as they are challenging. Are we witnessing evidence that the Big Bang timeline itself needs to be fundamentally revised? Do these observations suggest that dark matter and dark energy behave in ways we haven't imagined? Are we seeing the signatures of cosmic processes that operate beyond the boundaries of known physics? As we continue to grapple with these mysteries, we find ourselves in the remarkable position of being the first generation of humans capable of directly observing the universe's earliest epochs. Webb has given us the ability to witness cosmic history as it actually unfolded, not as our theories predicted it should have unfolded. The universe has just revealed that it's far stranger, more dynamic, and more creative than we ever dared imagine. And we're only beginning to understand what that means for our place in the cosmic story and our ongoing quest to comprehend the deepest mysteries of existence itself. What makes these revelations even more unsettling is the growing realization that Webb might be showing us evidence of cosmic processes that operate entirely outside the boundaries of known physics. As astronomers have delved deeper into the telescope's data, they've begun to detect phenomena that seem to violate some of our most fundamental assumptions about how energy, matter, and space-time itself behave under extreme conditions. Consider the implications of finding mature stellar populations in galaxies that formed when the universe was barely 500 million years old. The red giant stars that Webb observes in these ancient systems represent the end stages of stellar evolution, objects that have exhausted their nuclear fuel and expanded into their final, bloated configurations. But the evolutionary pathway from a newly formed star to a red giant requires specific timescales that are dictated by the fundamental constants of physics. A star's lifetime is determined by its mass and the rate at which it can fuse hydrogen into helium in its core. This process is governed by the strong nuclear force, one of the four fundamental forces of nature. The fusion rates, the energy output, and the evolutionary timescales that result are not arbitrary. They're locked in by the basic structure of atomic nuclei and the quantum mechanical processes that govern nuclear reactions. Yet Webb is finding red giants in galactic environments that, according to our understanding of stellar physics, should contain nothing but young, hot, blue stars. It's as if we're discovering elderly oak trees in forests that were planted last Tuesday. The chronology simply doesn't work unless something fundamental about our understanding of stellar evolution is wrong. Some researchers have proposed that stars in the early universe might have evolved along entirely different pathways than their modern counterparts. The primordial cosmos was a very different place, with higher densities, different chemical compositions, and possibly even different values for some of the fundamental constants that govern physical processes. If the rate of nuclear fusion was accelerated in the early universe, perhaps due to higher ambient radiation fields or exotic matter interactions, stars could have evolved much more rapidly than current models predict. Alternatively, the first generation of stars might have been fundamentally different objects entirely, with internal structures and evolutionary pathways that have no modern analogues. But even these exotic possibilities struggle to account for the full spectrum of anomalies that Webb continues to reveal. The telescope has detected objects that appear to be generating far more energy than any known physical process should allow, given their apparent masses and ages. These cosmic lighthouses are shining with luminosities that approach theoretical limits for matter-to-energy conversion, suggesting either that we're misunderstanding their true nature or that they're powered by mechanisms we haven't discovered. Among the most perplexing of these ultraluminous objects are sources that appear to be varying in brightness over timescales that seem impossibly short. When an object changes its luminosity, the variation can't propagate faster than the speed of light across the entire structure. This creates a fundamental limit. An object that varies significantly over the course of days or weeks can't be larger than a few light days or light weeks across. Yet some of Webb's variable sources appear to have luminosities that would require them to be much larger than their variation timescales allow. It's as if we're observing objects that are somehow circumventing the speed of light limit, coordinating their energy output across vast distances instantaneously. This represents a direct challenge to special relativity, one of the most thoroughly tested theories in all of physics. The discoveries become even more bewildering when we examine Webb's observations of the cosmic web itself, the vast network of dark matter filaments that provides the scaffolding for all cosmic structure. Computer simulations of structure formation predict that this web should emerge gradually, with small-scale structures forming first and larger structures assembling over billions of years through a process of hierarchical growth. But Webb reveals a cosmic web that appears to have organized itself much more rapidly and completely than these simulations predict. The telescope can trace individual filaments of dark matter stretching across hundreds of millions of light years, connecting massive galaxy clusters in patterns that seem far too organized and extensive for the age of the universe. This suggests that either dark matter behaves very differently than our current models assume, or that there were initial conditions in the early universe that we don't understand. Dark matter makes up roughly 85% of all matter in the cosmos, yet we know almost nothing about its fundamental nature. We infer its existence from its gravitational effects, but we have no direct knowledge of what dark matter particles are, or how they interact with each other, or with ordinary matter. Webb's observations hint that dark matter might have properties that allow it to organize itself into large-scale structures much more efficiently than current theories predict. Perhaps dark matter particles interact with each other through forces we haven't discovered, enabling them to clump together and form cosmic structures at accelerated rates. Alternatively, dark matter might interact with the fabric of spacetime itself in ways that our current understanding of general relativity doesn't capture. Einstein's theory describes gravity as the curvature of spacetime caused by matter and energy, but it was developed and tested primarily in the relatively weak gravitational fields of our solar system. The extreme conditions of the early universe represent a regime where general relativity has never been directly validated. Some theoretical physicists have proposed modifications to Einstein's equations that could account for the apparent effects of dark matter without requiring exotic new particles. These modified theories of gravity suggest that the gravitational force itself might behave differently on cosmic scales or under extreme conditions, providing mechanisms for accelerated structure formation that could explain Webb's observations. But perhaps the most radical possibility is that Webb is revealing evidence of cosmic inflation operating on scales and timescales that we never anticipated. Inflation is the theoretical process that drove the exponential expansion of the universe during the first fraction of a second after the Big Bang, stretching quantum fluctuations to cosmic scales and creating the density variations that eventually grew into galaxies and galaxy clusters. Most models of inflation predict relatively modest initial density fluctuations, providing gentle seeds for structure formation that would grow gradually under the influence of gravity over billions of years. But some exotic models of inflation could produce much larger initial perturbations, creating density variations so extreme that massive structures could form almost immediately after the end of inflation. If such extreme inflation scenarios actually occurred, they could explain how massive galaxies and complex cosmic structures appeared so early in the universe's history. These models push inflation theory to its limits, invoking quantum field dynamics and energy scales that approach the boundaries of theoretical physics. The implications of these discoveries extend far beyond cosmology into the foundations of physics itself. If Webb's observations require new physics to explain, we might be witnessing the first direct evidence of phenomena that operate beyond the standard model of particle physics or outside the framework of general relativity. This possibility is both terrifying and exhilarating for the scientific community. Terrifying because it suggests that some of our most fundamental theories might be incomplete or incorrect. Exhilarating because it offers the prospect of revolutionary discoveries that could reshape our understanding of reality at the deepest level. Throughout the history of science, moments of crisis have often preceded periods of extraordinary progress. When observations began to conflict with Newton's laws of motion, the result was Einstein's theory of relativity. When classical physics failed to explain atomic phenomena, the result was quantum mechanics. When astronomical observations revealed that the universe was expanding, the result was the Big Bang theory. We might now be entering another such period of revolutionary change, where observations force us to abandon comfortable assumptions and venture into uncharted territory. Webb's discoveries could be the opening chapters of a new scientific revolution, one that will require us to develop entirely new theoretical frameworks to understand the cosmos. The psychological impact of these revelations on practicing astronomers cannot be overstated. Many have devoted their careers to developing and refining theoretical models that seem to successfully explain cosmic evolution. The apparent breakdown of these models in the face of Webb's observations creates a profound sense of intellectual vertigo, a feeling that the ground is shifting beneath decades of careful theoretical work. Yet there's also a sense of excitement and possibility that permeates the astronomical community. Scientists didn't become researchers to confirm what they already knew. They became scientists to discover new truths about the universe. Webb's observations, however challenging they might be to existing theories, represent exactly the kind of paradigm-shifting discoveries that make scientific careers worthwhile. The telescope continues to push deeper into cosmic history with each new observation, revealing layers of complexity that no one anticipated. Recent deep-field observations have detected sources of light from epochs when the universe was only 100 million years old, pushing back the boundaries of the observable cosmos to times when the first stars were supposedly just beginning to ignite. These ultra-distant sources appear as tiny points of blue light, the signatures of massive hot stars that somehow managed to form in the primordial darkness. But their very existence raises profound questions about the timeline of cosmic rionization, the process by which the first stars and galaxies cleared the fog of neutral hydrogen that filled the early universe. Current models predict a gradual process, unfolding over hundreds of millions of years as the first stars slowly ionized the surrounding gas. But Webb's detection of organized stellar structures at such early epochs suggests that rionization might have proceeded much more rapidly and efficiently than these models predict. The implications cascade through our understanding of cosmic evolution. If rionization occurred earlier and more rapidly than expected, it would have created very different conditions for subsequent galaxy formation. The cleared regions around early stellar sources would have provided environments where gas could cool and collapse more efficiently, potentially explaining how massive galaxies could form so quickly in the early universe. But this explanation creates its own puzzles about the sources of rionization themselves. The first stars should have been massive, short-lived objects that burned through their nuclear fuel in just a few million years before exploding as supernovae. These stellar explosions would have enriched the surrounding gas with heavy elements, while simultaneously disrupting further star formation through their powerful shock waves. The balance between stellar birth and stellar death in the early universe should have created a complex feedback system that regulated the pace of cosmic evolution. Too much star formation would have led to excessive supernova feedback, shutting down further stellar birth. Too little would have failed to provide sufficient ionizing radiation to clear the neutral hydrogen fog. Webb's observations suggest that early stellar populations somehow managed to thread this needle with remarkable precision, forming stars at just the right rate to drive rapid rionization, while avoiding the feedback catastrophes that should have shut down the process. This delicate balance seems almost impossibly fine-tuned, raising questions about whether there were guiding principles or physical mechanisms that we don't understand operating in the early universe. Some researchers have begun to speculate that Webb might be revealing evidence of cosmic fine-tuning that goes beyond anything previously imagined. The fundamental constants of physics, the properties of dark matter and dark energy, and the initial conditions set by cosmic inflation might all have been precisely calibrated to allow the rapid emergence of complex cosmic structures. This possibility ventures into philosophical territory that makes many scientists uncomfortable. The apparent fine-tuning of physical constants to allow the existence of stars, planets, and life has long been a subject of debate, with some arguing that it points toward design or purpose in the universe, while others suggest it simply reflects selection effects in a multiverse of possibilities. Webb's discoveries add new dimensions to this debate by revealing that the fine-tuning might extend to the very timeline of cosmic evolution itself. If the universe hadn't evolved structures as rapidly as Webb observes, there might not have been enough time for the complex chemistry of life to develop before stellar evolution and cosmic expansion made such chemistry impossible. Yet even as these philosophical implications swirl through the scientific community, researchers continue to focus on the immediate challenge of understanding what Webb has shown them. The telescope generates enormous amounts of data with each observation, requiring sophisticated analysis techniques to extract meaningful scientific insights from the flood of information. Machine learning algorithms now play crucial roles in identifying unusual objects in Webb's images, flagging candidates for follow-up observations that might reveal new categories of cosmic phenomena. These artificial intelligence systems can process vast amounts of data far more quickly than human astronomers, but they also sometimes identify objects that challenge human understanding of what's possible in the universe. The collaboration between human insight and machine intelligence has become essential for making sense of Webb's discoveries. Computers can identify patterns and anomalies that human eyes might miss, while human astronomers provide the theoretical context and physical intuition needed to interpret these patterns meaningfully. This symbiotic relationship between human and artificial intelligence reflects a broader transformation in how astronomical research is conducted. Modern astronomy generates data at rates that far exceed human capacity to analyze, making computational assistance not just helpful, but essential for scientific progress. Webb's revelations also highlight the importance of international collaboration in addressing scientific challenges that transcend national boundaries. The telescope itself represents a partnership between NASA, the European Space Agency, and the Canadian Space Agency, with contributions from thousands of scientists, engineers, and technicians around the world. The analysis and interpretation of Webb's observations involve researchers from dozens of countries, bringing diverse perspectives and expertise to bear on questions that no single institution could address alone. This global scientific community represents humanity's collective effort to understand our place in the cosmos, transcending political and cultural differences in pursuit of universal truths. As Webb continues its observations and researchers struggle to understand its implications, we find ourselves in a remarkable position in human history. We are the first generation capable of directly observing the universe's earliest epochs, witnessing cosmic evolution as it actually unfolded rather than as our theories predicted it should have unfolded. This privilege comes with profound responsibilities. The knowledge Webb provides about cosmic origins and evolution will shape human understanding for generations to come. The theoretical frameworks we develop to explain these observations will influence how future scientists approach questions about the nature of reality itself. The universe has just revealed that it operates according to principles we don't fully understand, following evolutionary pathways we never imagined, and achieving levels of complexity that challenge our most fundamental assumptions about cosmic development. We are witnesses to a revolution in human knowledge that may be as significant as any in our species' history. The story continues to unfold with each new Webb observation, each analysis of previously collected data, and each theoretical insight that emerges from the global community of researchers grappling with these mysteries. The impossible has become undeniable, and we are only beginning to comprehend what that means for our understanding of existence itself. The most unsettling aspect of these discoveries isn't just that they challenge specific astronomical theories, it's that they're forcing us to question the very nature of time itself in the cosmic context. When Webb peers into the deepest reaches of space, it's essentially functioning as a time machine, capturing photons that have been travelling toward us since the universe was barely recognizable as the cosmos we inhabit today. But what happens when that time machine reveals events that shouldn't have had enough time to occur? What happens when the universe's own historical record contradicts the timeline we've so carefully constructed from decades of theoretical work and observational evidence? This is precisely the existential crisis that Webb has thrust upon the astronomical community. The telescope isn't just finding objects that are larger or brighter than expected. It's finding objects that appear to exist in violation of causality itself, as if cosmic evolution somehow managed to skip ahead in its own timeline. Consider the fundamental physics involved in galaxy formation. When we observe a galaxy that contains hundreds of billions of mature stars, we're looking at the end result of countless individual processes that each require specific amounts of time to unfold. Gas clouds must collapse under their own gravity, a process that occurs at speeds determined by the fundamental constants of physics. Stars must form through nuclear ignition, a process governed by quantum mechanics and the strong nuclear force. Those stars must then evolve through their main sequence lifetimes, burning hydrogen at rates dictated by their masses and the efficiency of nuclear fusion. Each of these steps has characteristic timescales that cannot be arbitrarily compressed. They represent physical processes operating at their natural rates, constrained by the fundamental structure of reality itself. Yet Webb is observing galaxies that appear to have completed all these steps in a fraction of the time that physics suggests should be necessary. It's as if the universe found a way to accelerate its own development, operating in fast-forward mode during its earliest epochs before settling into the more leisurely pace of cosmic evolution that we observe in the modern cosmos. This possibility challenges not just our understanding of galaxy formation, but our comprehension of how time itself functions in extreme cosmic environments. Some theoretical physicists have begun exploring the possibility that the flow of time might have been different in the early universe. Einstein's general relativity tells us that time is not absolute but relative, dependent on gravitational fields and the motion of observers. In the extreme conditions that existed shortly after the Big Bang, when matter was compressed to unimaginable densities and temperatures reached levels that dwarf the cores of the most massive stars, the very fabric of space-time might have behaved in ways we've never considered. Perhaps time itself flowed more rapidly in the early universe, allowing cosmic evolution to proceed at accelerated rates that would be impossible under modern conditions. This isn't just speculative philosophy, but a legitimate area of theoretical investigation, as researchers explore how extreme gravitational fields and exotic matter states might affect the fundamental structure of space-time. The implications extend far beyond astronomy into the deepest questions about the nature of reality. If time can flow at different rates under different cosmic conditions, what does that mean for our understanding of causality, of the relationship between cause and effect that underpins all scientific reasoning? If the early universe operated according to different temporal rules than the cosmos we inhabit today, how can we hope to understand its evolution using theories developed in our present-day context? These questions become even more profound when we consider Webb's discovery of what astronomers have begun calling fossil galaxies, ancient stellar systems that appear to have completed their entire evolutionary cycle when the universe was still in its supposed infancy. These objects show all the characteristics of elderly galaxies: depleted gas reserves, predominantly old stellar populations, and chemical signatures that speak of billions of years of stellar evolution and enrichment. Finding such evolved systems in the early universe is like discovering the ruins of ancient civilizations in geological strata that predate the emergence of life itself. The chronology simply doesn't make sense unless our fundamental understanding of cosmic timelines is profoundly incomplete. The chemical evidence is particularly compelling and disturbing. When Webb analyzes the light from these ancient galaxies, it reveals spectral signatures of elements that should not exist in significant quantities so early in cosmic history. Oxygen, carbon, silicon, iron, all the heavy elements that form the basis of planetary systems, and ultimately, life itself, appear in abundances that require multiple generations of stellar evolution to produce. This chemical complexity tells a story of cosmic recycling that should have unfolded over billions of years. Massive stars must have formed, lived their brief but brilliant lives, and died in spectacular supernova explosions that scattered their nuclear ashes throughout space. Subsequent generations of stars must have incorporated these heavy elements, creating even more complex chemistry through their own evolutionary cycles. Gas clouds enriched with these stellar byproducts must have cooled and condensed, forming new stellar nurseries where planets could eventually coalesce from the accumulated debris of cosmic history. Each step in this chemical evolution requires specific timescales dictated by the physics of stellar nucleosynthesis, supernova dynamics, and gas cloud cooling rates. The fact that Webb observes such chemical richness in galaxies that formed when the universe was supposedly too young for these processes to have occurred suggests that cosmic chemical evolution proceeded far more rapidly than our theories predict. Some researchers have proposed that the first generation of stars, known as population 3 stars, might have been fundamentally different from anything we observe in the modern universe. These primordial giants, formed from the pristine hydrogen and helium left over from the Big Bang, might have been hundreds or even thousands of times more massive than typical contemporary stars. Such supermassive stars would have lived incredibly brief lives, perhaps only a few million years, before exploding as hypernovae with energies that make ordinary supernovae seem like firecrackers. These cosmic cataclysms could have instantly enriched vast regions of space with heavy elements, jump-starting the chemical evolution that normally requires billions of years to unfold gradually. But even this exotic scenario struggles to explain the full spectrum of chemical complexity that Webb observes in early galaxies. The ratios of different elements, the isotopic signatures, and the spatial distribution of heavy elements all point to multiple cycles of stellar birth, evolution, and death occurring within timeframes that seem impossibly compressed. The puzzle deepens when we consider the role of supermassive black holes in these early galactic systems. Webb has detected the signatures of actively feeding black holes in galaxies that formed when the universe was less than 1 billion years old. These cosmic monsters appear to have achieved masses millions or billions of times that of our Sun, despite existing in an epoch when there shouldn't have been enough time for such massive objects to grow. Supermassive black holes grow primarily through two mechanisms: the gradual accretion of surrounding matter and occasional mergers with other black holes. Both processes have characteristic timescales that depend on the availability of fuel and the efficiency of accretion mechanisms. Current models suggest that growing 1 billion solar mass black hole from stellar mass seeds should require several billion years, even under the most favourable conditions. Yet Webb finds evidence of such massive black holes in galaxies that formed when the universe was only a fraction of its current age. These objects appear to have grown at rates that approach or exceed theoretical limits for black hole accretion, suggesting either that our understanding of black hole physics is fundamentally incomplete, or that entirely different formation mechanisms were operating in the early universe. One possibility involves the direct collapse of primordial gas clouds into massive black holes, bypassing the usual stellar intermediary stage entirely. Under the right conditions, gas clouds with masses hundreds of thousands of times that of the Sun might collapse directly into black holes without first forming stars. These direct collapse black holes could provide the massive seeds needed for rapid subsequent growth. But direct collapse requires very specific environmental conditions that should have been rare in the early universe. The gas must be kept warm enough to avoid fragmentation into smaller clumps, typically requiring intense radiation fields from nearby sources. Yet these radiation fields must not be so intense that they completely prevent the gas from cooling and collapsing. Threading this needle should have been extraordinarily difficult in the chaotic environment of the early cosmos. The fact that Webb observes numerous supermassive black holes in early galaxies suggests that either direct collapse was much more common than theoretical models predict, or that there were entirely different mechanisms for rapid black hole formation that we haven't discovered. Some researchers have even speculated about the possibility of primordial black holes formed in the immediate aftermath of the Big Bang, exotic objects that could have provided ready-made seeds for subsequent growth. These primordial black holes would represent relics of the universe's earliest moments, formed from density fluctuations during cosmic inflation or other exotic processes operating in the first fraction of a second after the Big Bang. If such objects existed in significant numbers, they could explain how supermassive black holes achieved their enormous masses so quickly in the early universe. But primordial black holes remain hypothetical objects, predicted by some theoretical models, but never directly observed. Their existence would require specific conditions during cosmic inflation that push the boundaries of what we understand about the universe's earliest moments. The fact that Webb's observations seem to demand their existence represents another challenge to our theoretical frameworks. The cumulative weight of these discoveries is creating what some astronomers have begun calling a cosmological crisis, a fundamental breakdown in our understanding of how the universe evolved from its initial simplicity to its current complexity. Every new Webb observation seems to reveal additional layers of cosmic organization that shouldn't have had time to develop. Additional evidence that the early universe was far more active, efficient, and creative than our theories allow. This crisis extends beyond specific objects or phenomena to challenge the entire framework of cosmic evolution that has guided astronomical research for decades. The hierarchical model of structure formation, which describes how small objects merge to form larger ones over cosmic time, appears to be inadequate for explaining what actually occurred in the early universe. Instead of gradual bottom-up assembly, Webb reveals what appears to be rapid top-down organization, with massive, complex structures appearing almost fully formed in the cosmic dawn. This suggests that the universe might have employed fundamentally different organizational principles during its youth, principles that we don't understand and that might not operate under modern conditions. The implications reach into the foundations of physics itself. If Webb's observations require new physics to explain, we might be witnessing the first direct evidence of phenomena that operate beyond our current theoretical frameworks. Modified theories of gravity, exotic properties of dark matter, quantum effects operating on cosmic scales. All these possibilities and more are being seriously considered by researchers struggling to make sense of what Webb has revealed. Some of the most radical proposals involve modifications to Einstein's general relativity itself. While general relativity has been extensively tested in the solar system and in other nearby cosmic environments, the extreme conditions of the early universe represent a regime where the theory has never been directly validated. Perhaps gravity behaves differently under such conditions, enabling rapid structure formation that would be impossible according to our current understanding. Alternative theories of gravity, developed originally to explain the apparent effects of dark matter and dark energy, might provide mechanisms for accelerated cosmic evolution that could account for Webb's observations. These modified gravitational theories suggest that the attractive force between masses might be stronger in certain environments or under specific conditions, allowing structures to form and grow much more rapidly than general relativity predicts. Other researchers have focused on the mysterious nature of dark matter itself. This invisible substance, which comprises roughly 85% of all matter in the universe, might have properties that we've never suspected. Perhaps dark matter particles interact with each other through forces we haven't discovered, enabling them to clump together and form large-scale structures much more efficiently than current models suggest. The possibility that dark matter behaves differently than we assume has profound implications for our understanding of cosmic structure formation. If dark matter can organize itself more rapidly than our theories predict, it could provide the gravitational scaffolding needed for accelerated galaxy formation in the early universe. Some theoretical models propose that dark matter might undergo phase transitions under certain conditions, changing its fundamental properties as the universe evolved. Perhaps dark matter was more interactive in the early universe, allowing it to form structures quickly before transitioning to the nearly collisionless state we observe today. These speculations push the boundaries of particle physics into regimes where our theoretical understanding becomes uncertain. Dark matter remains one of the greatest mysteries in modern physics, and Webb's observations suggest that this mystery might be even deeper than we realized. The role of cosmic inflation in setting up the initial conditions for structure formation has also come under renewed scrutiny. Inflation is thought to have stretched quantum fluctuations in the primordial universe to cosmic scales, creating the density variations that eventually grew into galaxies and galaxy clusters under the influence of gravity. Most models of inflation predict relatively modest initial density fluctuations, providing gentle seeds for structure formation that would grow gradually over billions of years. But perhaps some exotic models of inflation could produce much larger initial perturbations, giving structure formation a dramatic head start that would allow massive galaxies to form much earlier than conventional theories predict. These extreme inflation scenarios invoke quantum field dynamics and energy scales that approach the fundamental limits of theoretical physics. They represent our most speculative attempts to understand the universe's earliest moments, when the laws of physics themselves might have been different from what we observe today. The exploration of such exotic possibilities highlights how Webb's discoveries are pushing astronomy into uncharted theoretical territory. We're being forced to consider mechanisms and processes that operate far beyond our direct experience, in regimes where the familiar laws of physics might break down or behave in unexpected ways. Yet even as researchers grapple with these theoretical challenges, Webb continues to generate new discoveries that add fresh layers to the mystery. Recent observations have detected objects that appear to be changing their properties over timescales that seem impossibly short, suggesting dynamic processes operating at rates that challenge our understanding of cosmic evolution. The telescope has also revealed unexpected correlations between different types of cosmic structures, connections that hint at underlying organizational principles that we don't understand. Galaxy clusters, individual galaxies, and even stellar populations within galaxies all seem to follow patterns that suggest coordinated evolution on scales ranging from stellar systems to cosmic superclusters. These correlations point toward a universe that is far more interconnected and dynamically active than our theories suggest. Instead of isolated objects evolving independently according to local conditions, cosmic structures appear to be participating in a vast, coherent dance of evolution that spans the entire observable cosmos. The recognition of this cosmic choreography represents perhaps the most profound shift in our understanding of the universe that Webb has initiated. We're beginning to see the cosmos not as a collection of separate objects evolving in isolation, but as a unified system where every component influences and is influenced by the larger whole. This holistic view of cosmic evolution challenges the reductionist approach that has dominated physics for centuries. The assumption that we can understand complex systems by studying their individual components in isolation. Webb suggests that cosmic evolution might be an emergent phenomenon that can only be understood by considering the universe as an integrated whole. The philosophical implications are staggering. If the universe operates as a unified system rather than a collection of independent parts, what does that mean for our understanding of causality, of the relationship between local and global phenomena, of the very nature of existence itself? These questions venture into territory where astronomy, physics, and philosophy converge, where scientific observation meets fundamental questions about the nature of reality. Webb has not just shown us new objects in the cosmos, it has revealed that the cosmos itself might be fundamentally different from what we imagined. As we stand at this threshold between the known and the unknown, between comfortable certainty and revolutionary possibility, we find ourselves witnesses to one of the most significant moments in the history of human knowledge. The universe has just revealed that it operates according to principles we don't understand, following patterns we never suspected, and achieving levels of organization that challenge our most basic assumptions about existence itself. The journey of discovery continues with each new observation, each theoretical insight, and each moment of wonder as we confront the magnificent mystery of a universe that refuses to conform to our expectations. Webb has shown us that we live in a cosmos far stranger, more dynamic and more beautiful than we ever dared imagine, and we are only beginning to glimpse the full scope of its secrets. The psychological weight of these revelations extends far beyond the walls of observatories and university departments. We're living through a moment that future historians of science may mark as the beginning of a new era in human understanding, comparable to the moments when Galileo first pointed his telescope at Jupiter's moons, or when Edwin Hubble discovered that the universe was expanding. But unlike those previous revolutions, which primarily changed our understanding of our place in the cosmos, Webb's discoveries are forcing us to question the very nature of cosmic time itself. When we peer into the deepest reaches of space with this remarkable instrument, we're not just looking at distant objects. We're witnessing events that occurred when the universe was barely recognizable as the ordered cosmos we see today. The light reaching Webb's detectors began its journey when the universe was perhaps 3 or 4% of its current age. These photons have been traveling through expanding space for over 13 billion years, carrying within their spectral signatures the fossil record of cosmic conditions that existed in an almost alien version of reality. What that ancient light reveals challenges not just our theories, but our intuitive understanding of how time and causality operate on cosmic scales. Picture trying to solve a mystery where the evidence keeps arriving in the wrong order, where effects seem to precede their causes, where the final chapters of a story appear before the opening paragraphs have been written. This is the interpretive challenge that Webb has thrust upon astronomers around the world. The telescope is showing us mature cosmic structures in epochs when those structures should barely have begun to form. The most fundamental challenge lies in understanding how massive galaxies achieved their observed properties so quickly after the Big Bang. Galaxy formation isn't a simple process that can be arbitrarily accelerated. It requires a complex sequence of physical processes, each with characteristic timescales that are dictated by the fundamental constants of nature. First, dark matter must clump together under its own gravitational attraction, creating the invisible scaffolding upon which ordinary matter can accumulate. This process is constrained by the expansion rate of the universe and the initial density fluctuations left over from cosmic inflation. Computer simulations suggest that building substantial dark matter halos should require hundreds of millions of years at minimum. Next, ordinary matter in the form of primordial gas must fall into these dark matter wells, cooling and condensing despite the intense radiation environment of the early universe. This cooling process is governed by atomic physics and the availability of heavy elements that can radiate away thermal energy efficiently. In the early universe, with its limited supply of elements heavier than hydrogen and helium, gas cooling should have been extremely slow and inefficient. Only after these preliminary steps can the first stars begin to form, igniting nuclear fusion in their cores and beginning the long process of converting hydrogen into heavier elements. These first stellar generations must live out their entire life cycles, enriching their surroundings with the nuclear ashes of their fusion reactions before dying in spectacular supernova explosions. The heavy elements scattered by these stellar deaths must then be incorporated into subsequent generations of stars, creating increasingly complex stellar populations with the chemical diversity needed to form planetary systems. This multi-generational process of stellar birth, evolution, and death should require billions of years to produce the chemically mature galaxies that Webb observes in the early universe. Yet the telescope reveals galaxies that appear to have completed this entire evolutionary sequence when the universe was less than 1 billion years old. It's as if we're discovering the ruins of advanced civilizations in archaeological layers that should contain nothing but the simplest stone tools. The chronology defies explanation within our current theoretical frameworks. The spectroscopic evidence is particularly compelling and troubling. When Webb analyzes starlight from these ancient galaxies, it reveals chemical signatures that tell the story of multiple generations of stellar evolution. The presence of carbon, oxygen, nitrogen, and even heavier elements like silicon and iron indicates that numerous cycles of star formation and stellar death must have occurred to produce such chemical richness. Each of these elements has its own nuclear story. Carbon is forged in the hearts of intermediate mass stars through the triple alpha process, where 3 helium nuclei combine in a reaction so improbable that it seems almost miraculous. Oxygen requires even more massive stars, formed through the fusion of carbon and helium in stellar cores hot enough to overcome enormous nuclear barriers. Iron represents the endpoint of stellar nuclear synthesis, created in the final moments before massive stars collapse into supernova. Finding all these elements in significant abundances in early galaxies implies a level of stellar processing that should require vast amounts of time. The stars that created these elements must have had time to evolve from their initial formation through their entire main sequence lifetimes before dying and releasing their nuclear products into space. The timescales involved are not arbitrary, but are set by the fundamental physics of nuclear fusion and stellar structure. The mystery deepens when we consider the spatial distribution of these heavy elements within early galaxies. Webb's observations reveal that the chemical enrichment is not confined to small regions around individual stellar nurseries, but appears to be distributed throughout entire galactic systems. This suggests that the heavy elements had time to mix and spread through galactic-scale gas flows, a process that should require additional millions or hundreds of millions of years. Some of the most puzzling objects discovered by Webb appear to exist at the very edge of what current physics suggests should be possible. Among these are sources that astronomers have nicknamed impossible early galaxies, cosmic structures so massive and so well organized that their existence seems to violate fundamental principles of hierarchical structure formation. Hierarchical structure formation is one of the most successful theoretical frameworks in cosmology, describing how small density fluctuations in the early universe gradually grew into the cosmic web of galaxies and galaxy clusters we observe today. According to this model, structure formation should proceed from the bottom up, with small objects forming first and then merging to create increasingly larger structures over cosmic time. The model predicts that the most massive galaxies should be relatively rare in the early universe, forming only after billions of years of gradual assembly from smaller components. Yet Webb finds massive galaxies that appear to have assembled themselves when the universe was still in its supposed infancy, before the hierarchical process should have had time to build such large structures. These discoveries are forcing astronomers to confront the possibility that hierarchical structure formation might be an incomplete description of cosmic evolution. Perhaps there were additional mechanisms operating in the early universe that could accelerate structure formation beyond what the standard model predicts. Or perhaps the initial conditions set by cosmic inflation were very different from what we've assumed, providing much larger seeds for structure formation than current models suggest. The role of supermassive black holes in these early galactic systems adds another layer of complexity to the puzzle. Webb has detected the signatures of actively feeding black holes in galaxies that formed when the universe was less than 700 million years old. These cosmic monsters appear to have achieved masses millions of times that of our Sun, despite existing at epochs when there shouldn't have been enough time for such massive objects to grow. Supermassive black holes are thought to grow through a combination of gas accretion and mergers with other black holes. Both processes have characteristic timescales that depend on the availability of fuel and the efficiency of accretion mechanisms. Even under the most favourable conditions, growing a million solar mass black hole from stellar mass seeds should require hundreds of millions of years. The discovery of such massive black holes in early galaxies suggests either that black hole growth proceeded much more rapidly in the primordial universe, or that there were alternative formation pathways that bypassed the usual evolutionary bottlenecks. Some researchers have proposed that primordial black holes formed directly from density fluctuations in the immediate aftermath of the Big Bang could provide the massive seeds needed for rapid subsequent growth. But primordial black holes remain hypothetical objects, predicted by some theoretical models but never definitively observed. Their existence would require specific conditions during cosmic inflation that push the boundaries of what we understand about the universe's earliest moments. The fact that Webb's observations seem to demand exotic formation mechanisms represents another challenge to our theoretical frameworks. Perhaps even more unsettling is Webb's discovery of what appear to be organized galactic structures in the cosmic dawn. The telescope has revealed numerous examples of spiral galaxies, complete with well-defined disk structures and organized rotation patterns, existing when the universe was supposedly too young and chaotic for such delicate arrangements to form or survive. Spiral galaxies, like our own Milky Way, are marvels of cosmic engineering, with density waves propagating through their disks to organize stellar birth and maintain structural coherence across hundreds of thousands of light-years. These patterns are easily disrupted by gravitational encounters with other galaxies or by the violent feedback from stellar explosions and black hole activity. Current theories predict that the early universe should have been a hostile environment for spiral structures, filled with frequent galactic mergers and interactions that would have prevented the formation of organized disk galaxies. The high density of matter in the young cosmos should have created conditions where galaxies collided and merged so frequently that stable spiral patterns could never establish themselves. Yet Webb reveals early spiral galaxies that appear to have formed their organized structures and maintain them despite existing in what should have been a chaotic environment. This discovery suggests either that the early universe was far more stable than our models predict, or that spiral galaxies are much more resilient to disruption than we've assumed. The implications extend to our understanding of dark matter, the invisible substance that provides the gravitational scaffolding for all cosmic structure. If spiral galaxies could form and survive in the early universe, it suggests that dark matter halos were already well organized and stable at very early epochs, contrary to theoretical expectations about the gradual assembly of cosmic structure. Some researchers have proposed that these observations might require modifications to our understanding of dark matter itself. Perhaps dark matter particles interact with each other through forces we haven't discovered, enabling them to organize into stable structures much more rapidly than current models predict. Alternatively, dark matter might have undergone phase transitions in the early universe that altered its clustering properties in ways we don't understand. The cumulative weight of these discoveries is creating what some cosmologists have begun calling a timeline crisis in our understanding of cosmic evolution. Every aspect of early cosmic history, from the formation of the first stars to the assembly of the first galaxies, appears to have proceeded much more rapidly than our theories suggest should be possible. This crisis extends beyond specific objects or phenomena to challenge the fundamental assumptions underlying modern cosmology. The age of the universe, the rate of cosmic expansion, the properties of dark matter and dark energy, the nature of cosmic inflation, all these pillars of the standard cosmological model are being scrutinized in light of Webb's revelations. Some researchers have begun exploring the possibility that the universe itself might be older than we've calculated, providing additional time for the complex evolutionary processes that Webb observes in early galaxies. This would require revisions to our measurements of cosmic expansion rates and our understanding of the relationship between distance and redshift for the most remote objects. Others have focused on the possibility that cosmic inflation created initial conditions very different from what standard models predict. Perhaps the quantum fluctuations that seeded structure formation were much larger than we've assumed, or perhaps there were additional physical processes during inflation that created more favorable conditions for rapid structure formation. The most radical proposals involve modifications to the fundamental constants of physics themselves. Perhaps the strength of gravitational attraction was different in the early universe, allowing structures to form more rapidly than would be possible under modern conditions. Or perhaps the rate of nuclear fusion in early stars was enhanced by exotic physical conditions that no longer exist. These speculations push the boundaries of theoretical physics into regimes where our understanding becomes uncertain and untested. We're being forced to consider possibilities that would have seemed like science fiction just a few years ago, yet they represent serious attempts by leading researchers to reconcile Webb's observations with the laws of physics. The telescope's discoveries also highlight the remarkable precision required for any successful theory of cosmic evolution. The universe appears to have navigated an incredibly narrow path between chaos and order, achieving just the right balance of conditions to allow complex structures to form without triggering runaway processes that would have prevented further evolution. If star formation had proceeded too rapidly in early galaxies, the resulting supernova feedback would have blown away the gas needed for continued stellar birth. If it had proceeded too slowly, there wouldn't have been enough stellar energy to ionize the neutral hydrogen that filled the early universe. If supermassive black holes had grown too quickly, their energetic outflows would have shut down galaxy formation entirely. If they had grown too slowly, they couldn't have influenced their host galaxies' evolution. The fact that cosmic evolution threaded all these needles simultaneously, achieving just the right balance to produce the complex universe we observe today, suggests either remarkable fine-tuning or the operation of physical principles we don't understand. Either possibility has profound implications for our understanding of the cosmos and our place within it. Webb's continuing observations promise to reveal even more surprises as the telescope pushes deeper into cosmic history. Recent observations have detected candidate objects at redshifts that correspond to times when the universe was only 150 million years old, pushing back the boundaries of the observable cosmos to epochs when the first stars were supposedly just beginning to ignite. These ultra-distant sources appear as faint smudges of light in Webb's deepest images, but their very existence at such early epochs challenges our understanding of when and how the first stellar populations could have formed. If confirmed, they would represent the earliest known sources of light in the universe, beacons from the cosmic dawn that illuminate conditions during the universe's emergence from its dark age. The spectroscopic analysis of these ultra-distant sources reveals signatures that are both familiar and alien. The light shows evidence of hydrogen and helium, the primordial elements left over from the Big Bang, but also hints of heavier elements that shouldn't exist in significant quantities so early in cosmic history. Each new spectrum adds pieces to a puzzle that grows more complex and mysterious with every observation. As astronomers continue to grapple with these revelations, they're discovering that Webb has fundamentally changed not just our knowledge of the early universe, but our relationship with cosmic mystery itself. The telescope has revealed that the universe is far stranger, more dynamic, and more creative than we ever imagined, operating according to principles that we're only beginning to glimpse. This realization is both humbling and inspiring. Humbling because it reminds us how much we still don't know about the cosmos we inhabit. Inspiring because it reveals that the universe still holds secrets capable of surprising and delighting us, still contains mysteries worthy of our greatest intellectual efforts and technological achievements. The story of Webb's discoveries is ultimately a story about the power of human curiosity and ingenuity to reveal truths about existence that seemed forever beyond our reach. The telescope represents the culmination of decades of technological development, international cooperation, and scientific dedication, all focused on the singular goal of understanding our cosmic origins. Yet even as we celebrate these remarkable achievements, Webb reminds us that every answer leads to new questions, every discovery opens up fresh mysteries, every breakthrough reveals how much more there is to learn. The universe has just shown us that it operates according to rules we don't understand, follows patterns we never suspected, and achieves levels of organization that challenge our most fundamental assumptions about reality itself. We stand at the threshold of a new era in cosmic understanding, witnesses to revelations that may reshape human knowledge for generations to come. The impossible has become undeniable, the theoretical has become observational, and the universe has revealed itself to be far more magnificent and mysterious than we ever dared imagine. The implications of these discoveries extend far beyond the realm of academic astronomy into questions that touch the very foundations of human understanding. We're not simply dealing with a few unusual objects that don't quite fit our models. We're confronting evidence that suggests our entire framework for understanding cosmic evolution might be fundamentally incomplete. Consider what it means to be wrong about something as basic as the timeline of the universe itself. For decades, we've operated under the assumption that we understand the broad strokes of cosmic history. The Big Bang occurred 13.8 billion years ago. The first stars ignited roughly 400 million years later. Galaxies began as small primitive collections of these early stars and gradually grew larger and more complex through mergers and accretion over billions of years. This narrative wasn't just theoretical speculation, it was built on careful observations, sophisticated mathematical models, and our best understanding of fundamental physics. It represented the culmination of centuries of scientific progress, from Newton's laws of motion to Einstein's theory of relativity to the quantum mechanical principles that govern stellar nucleosynthesis. Yet Webb is revealing a universe that seems to have ignored this carefully constructed timeline entirely. Instead of the gradual bottom-up assembly that hierarchical structure formation predicts, we're seeing evidence of rapid top-down organization, where massive, complex systems appear almost fully formed in the cosmic dawn. The psychological challenge for the scientific community cannot be overstated. Imagine spending your career developing theoretical frameworks that seem to successfully explain the observable universe, only to discover that your fundamental assumptions about cosmic chronology might be wrong. It's like being a historian who discovers that the Renaissance actually preceded the Middle Ages, or a biologist who finds evidence that complex multicellular life appeared before single-celled organisms. This isn't just about adjusting parameters in existing models or refining theoretical predictions. Webb's discoveries are forcing astronomers to question whether the basic conceptual framework that has guided cosmological research for generations is adequate to describe reality. The telescope is revealing a universe that operated according to rules we don't understand, achieved organizational complexity through mechanisms we haven't discovered, and followed evolutionary pathways that our theories never anticipated. The challenge becomes even more profound when we consider the interconnected nature of cosmological theories. Our understanding of galaxy formation depends on our models of dark matter clustering, which in turn rely on our theories about cosmic inflation and the early universe's conditions. Our calculations of stellar evolution timescales are based on fundamental physics constants that we assume remained constant throughout cosmic history. Our interpretations of cosmic distances and ages depend on our understanding of how space itself has expanded since the Big Bang. If Webb's observations require us to revise any of these foundational assumptions, the ripple effects could propagate throughout our entire understanding of cosmic evolution. We might need to reconsider not just how galaxies form, but how the universe itself has evolved from its initial state to its current configuration. Some researchers have begun exploring modifications to cosmic inflation theory that could account for Webb's observations. Standard models of inflation predict relatively modest density fluctuations in the early universe, providing gentle seeds for structure formation that would grow gradually under gravitational attraction over billions of years. But perhaps more exotic inflation scenarios could have produced much larger initial perturbations, giving structure formation a dramatic head start. These extreme inflation models push the boundaries of theoretical physics, invoking quantum field dynamics and energy scales that approach the fundamental limits of what we can meaningfully discuss. They represent our most speculative attempts to understand processes that occurred in the first fraction of a second after the Big Bang, when the universe was smaller than an atomic nucleus and governed by physics that may have been very different from what we observe today. The possibility that inflation created much larger density fluctuations than standard models predict would have profound implications for our understanding of the universe's earliest moments. It would suggest that the primordial cosmos was far more violent and dynamic than we've assumed, with quantum fluctuations achieving amplitudes that dwarf anything in our current theoretical frameworks. Such extreme initial conditions could potentially explain how massive galaxies formed so quickly in the early universe. If inflation left behind density peaks that were orders of magnitude larger than standard models predict, these enhanced fluctuations could have collapsed under their own gravity much more rapidly, forming the first stellar nurseries when the universe was still in its supposed infancy. But even these exotic inflation scenarios struggle to explain the full spectrum of organization and complexity that Webb observes in early galaxies. The chemical signatures, the stellar populations, the evidence of multiple generations of star formation and evolution all suggest processes that should require substantial time to unfold, even with enhanced initial conditions. This has led some theoretical physicists to consider even more radical possibilities, including modifications to our understanding of fundamental physics itself. Perhaps the constants of nature weren't actually constant in the early universe. Maybe the strength of gravitational attraction was different when the cosmos was young and dense, allowing structures to form more rapidly than would be possible under modern conditions. The idea of varying fundamental constants isn't entirely unprecedented in theoretical physics. Some theories of quantum gravity suggest that what we perceive as fixed constants might actually be dynamic quantities that evolved as the universe expanded and cooled. If the gravitational constant was larger in the early universe, it could have accelerated structure formation beyond what current models predict. Similarly, if the rate of nuclear fusion was enhanced in primordial stellar cores, perhaps due to different physical conditions or exotic matter interactions, stars could have evolved through their life cycles much more rapidly than we observe today. This could explain how multiple generations of stellar evolution occurred within the compressed time frames that Webb's observations seem speculations to require. These venture into territory where established physics becomes uncertain and untested. We're considering modifications to the most fundamental aspects of reality, from the nature of space-time itself to the constants that govern atomic and nuclear processes. The fact that Webb's observations seem to demand such exotic explanations highlights just how revolutionary these discoveries have been. Yet even as researchers explore these theoretical frontiers, they must confront the possibility that the problem isn't with our physics, but with our observations. Could Webb be systematically misinterpreting what it's seeing, Could there be unknown sources of bias or error in the telescope's measurements that are creating the appearance of impossible early galaxies? The astronomical community has subjected Webb's observations to unprecedented scrutiny, checking and double-checking every aspect of the data reduction and analysis process. Multiple independent research teams have examined the same observations and reached similar conclusions about the properties of early galaxies. The telescope's instruments have been calibrated against known standards and cross-validated through observations of nearby objects, whose properties are well understood. This rigorous verification process makes systematic errors an unlikely explanation for Webb's discoveries. The observations appear to be genuine, representing real properties of real objects in the early universe, rather than artifacts of instrumental limitations or analytical mistakes. The universe really does seem to contain massive, well-organized galaxies at epochs when such objects should not exist according to our theoretical understanding. The implications extend beyond cosmology into fundamental questions about the nature of scientific knowledge itself. How confident can we be in theories that describe phenomena we could never directly observe until now? The early universe has been a theoretical playground for decades, with competing models validated primarily through their mathematical elegance and their ability to explain indirect observations rather than direct confirmation. Now that we can actually peer into the cosmic dawn and witness early galaxy formation in action, we're discovering that reality is far more complex and surprising than our theories predicted. This doesn't represent a failure of the scientific method, but rather its ultimate vindication. Science progresses through the constant interplay between theory and observation, with new discoveries forcing revisions to existing understanding and opening entirely new avenues of inquiry. The beauty of Webb's revelations lies not just in their challenge to existing theories, but in their demonstration of cosmic creativity, operating on scales we never imagined. The universe appears to be far more dynamic, inventive, and capable of rapid self-organization than we dared assume. The same cosmic processes that created these impossible early galaxies eventually led to the formation of our own solar system, our planet, and ultimately to the emergence of consciousness capable of contemplating its own origins. This perspective transforms Webb's discoveries from merely puzzling observations into profound statements about the nature of existence itself. We're not just looking at distant galaxies, we're witnessing the universe's earliest experiments in complexity and organization, its first tentative steps toward the rich tapestry of structure that would eventually give rise to stars, planets, and life. The telescope has revealed that even in its infancy, the cosmos was already demonstrating the creative potential that would eventually produce everything from spiral galaxies to DNA molecules to conscious beings capable of building space telescopes. The impossible galaxies that Webb observes represent the universe learning to be creative, discovering organizational principles that it would refine and elaborate over billions of years of subsequent evolution. As Webb continues its observations, pushing ever deeper into cosmic history, we can expect even more surprises that will further challenge our understanding of how the universe works. The telescope has already detected candidate objects at redshifts corresponding to times when the universe was barely 100 million years old, pushing back the boundaries of the observable cosmos to epochs that approach the end of the cosmic dark ages. These ultra-distant sources represent the earliest known light in the universe, beacons from the cosmic dawn that illuminate conditions during the universe's transition from its primordial simplicity to the beginnings of complex structure. Each new detection adds pieces to a puzzle that grows more intricate and mysterious with every observation. The journey we've taken tonight through the deepest mysteries revealed by humanity's most powerful observatory brings us to a profound realization. We stand at the threshold of a new era in human understanding, witnesses to a universe far more magnificent and mysterious than we ever dared imagine. Webb has shown us that the cosmos refuses to conform to our carefully constructed theories, that reality operates according to principles we're only beginning to glimpse. The impossible has become undeniable, reminding us that the greatest discoveries often come not from confirming what we think we know, but from having the courage to question everything. Tonight, somewhere in the cosmic darkness, ancient light continues its journey toward us, carrying secrets that will reshape human knowledge for generations to come. Keep looking up, keep wondering, and remember that in a universe this strange and beautiful, the next impossible discovery is always just one observation away.